Good morning. This presentation is about an overview of laser welding of metal forms, techniques, advantages and challenges by Costanza, Khoshnaw, Tata and Mehta. Metal forms are porous material and are increasingly used in industrial, structural and functional applications. Main properties depend on chemical composition, metallurgical aspects, processing morphology, and amount of porosity, cell size and shape. There are some challenges and difficulties encountered in welding and bonding metal forms from widely used in the production of complex shaped components. Problems are usually associated also with welding processes in metal forms, and are the reduction in mechanical properties in their metallic compound formation, microstructural inhomogeneity, and low fatigue strength. Laser welding technologies seem to be the most promising joining techniques, and this paper presents an overview on laser welding and joining techniques involving metal forms based on laser technology in similar and dissimilar combination with and without filler material. In the scheme is reported what is a metal form. When a gas is dispersed in a solid, we can get a solid form, a cellular solid. The porosity can be open, as reported on the images on the top right, or closed cell on the bottom right. Open cell copper 60 zinc 40 alloy foam have been laser welded by a 1 kilowatt continuous wave fiber laser. First preliminary welding test in the bottom plate configuration have been performed. Experiments of foams joining have been successfully carried out in the configuration lap joint. Foams were joined to 1 mm thick cold rolled plate of the same material placed on the top of the surface of the foam, and welding speeds were applied ranging from 5 to 20 mm per second. During welding, the processing speed influences the width of the molten zone, while only slight variations were observed in the case of the heat-affected zone. The mean width of the welded joint ranged between 0.36 and 0.58 mm, and the size of the heat-affected zone was estimated approximately at 4 mm for the lowest speed and 3.5 mm for the highest speed. The composition analysis did not reveal significant modification. At the end, we can conclude that the study showed as the welding using a fiber laser can be successfully employed for joining copper-based foams. Laser welding of Lotus-type porous iron has been performed. In the picture, a schematic view of the Lotus-type porous specimen showing different combination of welding directions and pore growth directions are reported. The well-bead surface of the Lotus-type porous iron is rough with pits, and thence were not depending on the pore growth direction, perpendicular, parallel, or parallel to the specimen surface. The phenomenon is ascribable to the volume reduction on melting the porous metal and blowing the remaining gas from the closed pores. The hardness of the well bead increased as compared to that of the base metal, whichever is the direction of the pores. Prevention of volume reduction due to melting the pores by providing the filler metal. Pretreatment for eliminating the remaining gas in the closed pores by treatment, and smaller diameters of the pores are required for ensuring successful fusion welding. In the pictures, two microstructure of the cross-section view of the weld metal A and the base metal B with 2 kilowatt laser power and 2 millimeter by minute welding speed are reported. In this slide, the results of the investigation of the fatigue strength of empty and foam-filled laser welding steel center beams are reported. The beams have been tested under 3-point bending for stiffness, ultimate strength, and fatigue. In the picture are reported on top laser welded steel the sandwich panels, and on the bottom, the reduction of the shear-induced local stresses due to the filling material. In this picture, a schematic presentation of the three-point bending test setup is reported. During fatigue failure mode, cracks were initiated and propagated at the less stake welds. Consequently, cohesive fracture occurs in the foam. Fatigue life improvement is far better than expected, as the load level at 2 million cycles was increased by a factor of 8.5 when the beams are filled with a low-density polyvinyl chloride foam. Filling technology is an effective technique to improve the fatigue strength of lightweight sandwich panels. The fatigue problems in laser welded sandwich panels are due to shear-induced strain, and these deformations are often very local in the plate domain. It is recommended that the filling of the sandwich panel is carried out only at the location of a out-of-plane shear opposite to the web plate direction. However, before applying such functional grading, an investigation on the underlying physics of crack propagation in three-dimensional plate structure is required. In the picture, a sketch of the process for laser forming and joining aluminum foam cores inside a hollow profile is reported. Forming process utilizing external laser radiation of a hollow steel profile containing two separated aluminum foam core mixed with a formable solid aluminum precursor is present. The process consists in irradiating by means of a CO2 laser beam the external surface of a stainless steel tube containing the resident foams and the solid foamable precursor. The laser beam is moved around the rotating surface of the tubular through a brushless motor. In this slide, the results are reported of laser foamed sample with power density 76 watt by square millimeter and interaction time 0.974 seconds. Three process parameters should be taken into account to obtain a sound foam: laser beam power density, interaction time, and the total amount of beam energy delivered to the workpiece. The computation of two graphs, laser beam power density versus interaction time, and process energy versus interaction time, were selected as optimized process parameters which can achieve good forming condition. Laser welding of sandwich panels. In shipbuilding, the replacement of plate structure by laser welded sandwich panels offer considerable advantages for the production as well as vessel operation. Surface flatness and high stiffness make these sandwich panels well suited to span large open areas such as accommodation desk, hoistable car desk, or to be used as supporting bulkheads and partition walls. A possible way to compare the merits of different sandwich configurations is to calculate the surface weight and the midpoint deflection, then finding out the structural performance as a ratio of them. The structural response of the panel would be dominated by a bending along the webs, and the midpoint deflection is determined at first by the bending stiffness. Due to the number of design variables and constraints, a structural optimization method based on moving asymptotes was implemented. It can be used to minimize the structural weight per square meter of a panel that has a typical accommodation deck configuration. Additional weight can be saved by injecting low-cost polyurethane foams to the cavities or by incorporating a more structural core with greater thickness and higher density, as the free span of the sandwich panel can be increased. Metal foams show a set of weldability problems mainly related to the intrinsic pore structure, phase transformations on fast cooling, and compositional variation in the heat-affected zone. Laser welding has been recognized as the most studied process due to the minimal thermal effect on the base materials, and a large number of experimental studies have been found and described. A detailed discussion has been devoted to this overview study through analyzing the microstructural changes observed and its influence on the mechanical properties in general and the fatigue behavior in particular of such weld. Both metal foams and sandwich panel laser welder have been discussed in this work. and final conclusion, specific areas that need to be addressed. So at first, in situ analysis of the mechanical behavior of welding joints for a better comprehension of the load transfer mechanism in different joint zones based on micromechanical models which take into account the microstructural changes induced by welding process. Adoption of new filler materials, interlayers, that need to be studied to increase the joining efficiency and weldability of metal foams, but also a better knowledge of the joining mechanisms based on thermodynamic calculation can be useful for the optimization of material selection for the interlayer. Point 3. The researchers can be attracted to join metal foams topic through combination of functional features alongside high thermal and electrical conductivity typical of copper-based systems. And further research, finally, on new base material combination are necessary, involving porous metals and the production of complex-shaped porous components. Thank you, and bye-bye. These are the 22 references of this paper.